Hello everyone! I just wanted to make a video here to walk you through the lab that we're going to do this week, as well as give you some background on how to solve some of the problems, okay? So for the background portion of it, let's say we have some data. We have some X and we have some Y data. And it's not always clear what the relationship between these data is going to be. Well, the easiest way to do that is to make a plot of the data. So here we just have a simple X and Y plot. So for instance, for X is 1, Y is 1.6, we can put that data point on our plot, and we do that for all of our data points. And we see here we have this nice kind of linear trend. Well, to help us mathematically determine that trend, we can do something called a best fit line. So I've drawn a best fit line here in red, and just as a reminder, the equation for a line is y equals mx plus b, where y is your vertical data, x is your horizontal data, m is your slope, and b is your y-intercept. Now, we're going to use a computer simulation to determine the mathematical values for the slope and for the y-intercept. So here I plugged in these numbers and I got a slope value of 0.49 and a y-intercept of 1.02. So I can plug those back into our equation for a line and I get y equals 0.49x plus 1.02. So let's say I wanted to know what the expected value is for y if x were 20. I don't have an x value of 20, but I could plug it in there, do a little bit of math, and that will tell me what my expected y value is going to be. It's not always obvious how to plot something. So let me walk you through some data that we're going to take in a simulation here later. And that is, we're going to time how long it takes to throw a ball up in the air to reach its highest point. So for a bunch of different initial velocities, let's say we throw it at 100, it takes 10 seconds to reach its highest point, 180, it's 20, and so on. So we do this experiment, we toss it in the air and time how long it takes to reach the highest point, and we got this table of data here. Well, how do we plot it? What do we plot on the x-axis, the y-axis? What does the slope mean? What does the intercept mean? Well, let me walk you through how we can figure that out. So we always want to start with a physics equation. Well, from one of our kinematic equations, we can use that the final velocity equals the initial velocity plus acceleration times time. Well, in this particular experiment, because we're on Earth, the acceleration is going to be that negative 9.8. And in our experiment, the final velocity is 0 because at the highest point, the final velocity is 0. So we can plug those in. Now for acceleration, I'm not going to plug in 9.8. I'm going to leave it as g because we're going to try to solve for this later. So for our acceleration is negative g, where g is that 9.8. So when we plug those in, our final velocity is 0. And the acceleration a is negative g. So I'm going to rearrange this equation, which will be more obvious here in a minute, to be that the initial velocity equals gt. So all I did is I added gt over to both sides. So here I've rewritten that a little bit larger, and I've added a plus 0 here to kind of make it a little bit more clear. Well, we want to figure out how to plot this data. Well, we know the equation for a line is y equals mx plus b. Well, if we look, these look very similar, do they not? So you see how that the y and the initial velocity are in the same position, and how the time t and x are in the same position? So if I were to plot all my initial velocity data on the y-axis and all of my time data on the x-axis, we can see that the slope should be that g value, and the y-intercept should be the expected value of 0. So let's go ahead and plot that. So on the horizontal axis, we're going to plot the time data. And on the vertical axis, we're going to plot the initial velocity data. We have numbers for all those. So here's our plot. So here's our time on the horizontal axis. And here's our initial velocity on the y vertical axis. And I plotted in all these green points from the data that we have. So from here, we do expect that the slope is going to be g, and the y-intercept should be the expected value of 0. So let's plot our best fit line. So we're going to use some computer software to do that for us. And so we get a value for our slope of the best fit line of 10.0, and a value of our y-intercept to be negative 5.2. Now again, remember I said that our expected value is g. Now we know that g is supposed to be 9.8, but we got 10. And we know that our y-intercept expected value is 0, but we got negative 5.2. And that's fine. So this is our experimental value for g. So other experiments may get a different value for g, and The one that's most trusted is the 9.8 meters per second squared, because they did a lot of work to try to remove as much uncertainty from their experiment as possible. But ours, maybe we didn't do that as well. And so our value is just going to be a little bit different. So this is our experimental value. In fact, due to uncertainty, it's okay and expected that the G value won't be exactly 9.8. And the y-intercept value will not always be exactly the expected value of 0 in this case. So this is the lab that we're going to be doing for this week. We have a computer simulation where you're going to be launching this ball up in the air at different initial speeds, and we're going to be measuring how long it takes to reach the highest point. So I'm going to give you a bunch of different initial velocities that you're going to use, and then in the simulation, you're going to time how long it takes to reach the highest point. So that's the acquiring data portion. I'm going to walk you through that here in a minute. Then you're going to plot the data. So just like before, this is the exact same situation. For the y-axis, we're going to plot the initial velocity. For the time axis, or for the x-axis, we're going to plot time. So we expect that g will be our slope and that the y-intercept will be 0. And there's a computer program that I'm also going to walk you through how to do that in a minute. And once you've done both of these, I want you to go to the modules for this week. And I just have an assignment there where you're going to be answering questions using both the plotted data here and the simulation. So let me walk you through that. So there's a link here in the module that's going to take you to this website where we're going to get our data. And there's a number of things that we need to change in order to make this work. The first thing is we can change the angle of the cannonball here, of the cannon, by clicking and rotating it. And we're going to fire it directly upwards. So be sure this says 90 degrees. Over here on the right, we're not going to be firing a cannonball. We're going to do a golf ball. So go ahead and change this to golf ball here. And we are going to add air resistance. So be sure to click air resistance here. This is going to add some uncertainty to our experiment. And then down here at the bottom right below the cannon is the initial speed. The first data point we want to get is for 10 meters per second. So let's go ahead and click that over to 10 meters per second. And this red button is going to launch the golf ball up in the air. So it shows a bunch of data points here. We can use this tool in the top right. We can click and drag it over. And we can hover this over to see different values here. Our one we're interested in is the very, very top. It tells us the time it takes to reach that point. So at 10 meters per second, it takes 1.01 seconds to reach the highest point, and that'll be our first point that we're going to be plotting. So when you do this, be sure that when this is set to 10 meters per second, that you also get this 1.01 seconds, just to verify that all the settings are still the same. So we can do this for some different values. Eventually, we're going to be increasing our initial speed all the way, but sometimes when you launch it here at really high speeds, it goes up and off the screen, and that's okay. We can just hit this little zoom out button until we can see it, and then we can drag this up to the highest point, and that will tell us that time to reach the highest point given that initial speed. Well, another link in the module is going to take you to the plotter. This is a Desmos plotter, and it's going to look like this. On the top left here, here are the velocities that I want you to plot. Again, remember we're plotting the initial velocities on the y-axis, and the x-axis here are the times. So that first time we launched at 10 meters per second, and we got a time of 1.01. And here you see that green dot, that is our first point, and this red line is the best fit line. You can also, in the top right, you can zoom out or zoom in if you would like to look around to kind of fit all your data in there. And right below the data is the best fit line parameters. So here it tells us that m, which is the slope, is 9.9, and b is 0. So as you add more data in here, as you continue your experiment, this slope value and this y-intercept value is going to change. So once you've filled all this in from your experiment, go ahead and open up the assignment questions for this week. You can go ahead and start answering those questions. Now those questions are going to be both on the plot, on the physics simulation that had you work here, as well as the linearization that I talked about at the beginning of this video. All right, let's get to it.